So how do we solve equations with variables on both sides? If there are variables on both sides of your equation, what you want to do is collect the variable terms on one side and collect the constant terms on the other side. Let's see how this works by doing some examples. So here's a problem with variables on both sides. I have 15 minus 2x equals negative 7x. There is an x on both sides. So I want to make all of my x's be on only one side. So I'm going to add 2x to each side, getting rid of the minus 2x over there on the left by canceling it out. And I'm left with 15 on that side equals negative 5x over here. I'll divide both sides by negative 5, which will cancel out here. And I get x equals negative 3. So I'm going to plug in negative 3 for x to check this answer. So I'll have 15 minus 2 times negative 3 equals negative 7 times negative 3. Well, 15 minus 2 times negative 3 will be negative 6. And negative 7 times negative 3 will get me 21. I'll change this guy to addition, so it becomes 15 plus 6, which equals 21. Both sides are equal, so my answer checks out. Let's try another one. So I've got negative 3x equals 2x plus 19. Currently, this side has a constant, and this side doesn't. So I'm going to leave this 19 over here. I'm going to get rid of the 2x by subtracting 2x. Have to do that to both sides. So negative 3x minus 2x will leave me with negative 5x, and I have equals 19. So I'm going to divide both sides by negative 5. And for my value of x, I get x equals negative 19 fifths, or I could do it as a mixed number. It'd be negative 3 and 4 fifths. So whichever you prefer. So I'm going to plug that back into my problem here, make sure that I check it and that it works out. So for my check, I'm putting in negative 3 times negative 19 fifths equals 2 times negative 19 fifths plus 19. So let's make sure that it works out here. So negative 3 really has a denominator of 1. So negative 3 times negative 19 is going to give me 57 over 5. 1 times 5 is 5. On this side, 2 times negative 19 is going to give me negative 38 fifths plus 19. So I could get a common denominator here. I've got 57 fifths on this side. I've got negative 38 fifths here. Plus, if I want to do 19 times 5 to get this numerator here, I'm going to get 95. And 95 minus 38, or negative 38 plus 95, is going to leave me with 57 fifths. So actually, both sides equal the same number, and my answer checks out. So let's look at another one here. We've got 2.5y plus 6 equals 4.5y minus 1. So I have a y variable on each side. So in order to solve this one, I'm going to subtract 2.5y from both sides. And that will, on this side, cancel out. So I'll be left with 6 equals 2y minus 1. So now that I've got my variable terms on one side, I'm going to do the same for my constants. I'm going to add 1 to each side here. So all my constants will be on the left, and I get 7 equals 2y. And then if I divide both sides by 2, I get y by itself, and y equals 3.5. Let's try another one here together. So for this one, we're going to have to do some distributing first, because right now the problem is just too complex to solve as is. So I'm going to have negative 2x plus negative 10. Over here I'll have 12 should make this add the opposite, plus negative 3x. Okay, so I'm going to try to get my variable terms on the same side first. So I want to, I'm going to get rid of this negative 3x by adding 3x, or doing positive 3x to both sides. Cancels out here. And here I'm left with now just a single x plus negative 10 equals 12. Now I'm going to get rid of this negative 10 by adding positive 10. And I get x equals 22. All right, so some equations don't have one solution. Most equations do, but some don't. Some equations will have no solution. Some will have infinitely many solutions, an infinite amount of solutions. So let's look at some of these special types of equations. So here I have 3 minus 4x equals negative 7 minus 4x. So I'm going to start by adding 4x to each side, because I'm going to get my variable terms on one side. Except when I do this, I notice that, oh, it cancels out here just like I wanted, but it also cancels out here, and I'm left with 3 equals negative 7, which is actually not a true statement. So here I have no solution. I end up with something that is not true. There is no number that I can put in for x that makes those two sides equal. So no solution is my final answer. On this side, I'm going to distribute here first to make a simpler expression over here on the right. So I'm going to keep my 6x plus 4. Over here, 4 times 3 is 12, 1 times 2 is 2, and 12 divided by 2 gives me 6x plus 4 times 1 is 4. Well, right here I'm noticing, hey, they're the exact same equation. I can keep going and I can subtract 6x here to try to get my variable terms on the same side, but they're both going to cancel out, and I'm going to get 4 equals 4, which is a true statement. But going back to here, when they're exactly the same, anything I put in for x is going to make them both equal. So this guy has infinitely many solutions. Anything will work in here that is a real number. So lots and lots and lots and lots of solutions. So let's look at a word problem where we may actually use an equation with variables on both sides to get our answer. So here we've got two identical circles, and they want to know what is the area of these circles. Well, to find the area of a circle, we use our formula, radius squared times pi. So I need to know the radius here. Well, I've got the radius of this one, but this one I have the full diameter. So if I take 4x and I cut it in half, I would get 2x. So a radius for this guy is just 2x. And since they're identical, that is equal to this guy's radius, which is x plus 2. So I can actually solve here and find the value of x. I'm going to subtract an x from this side and do the same to the other. So I get x equals 2. So I can plug that in now to my original. 2 plus 2 is 4, or 2 times 2 is 4. So the radius for these circles is actually 4. So now I can find their area. 4 squared times pi. Well, 4 squared is 16. So 16 pi is the area of each of these circles.